Okay. So let's begin with today's lecture. Now, before we formally go into the contents of today's lecture, we probably did it in the last lecture, but I'll go over it again. Given a n by n square matrix A, okay, this matrix is singular, that is, it's not invertible, its inverse does not exist if and only if there exists a non-zero vector x such that Ax equals 0. Okay, so symbolically, this matrix is singular if its determinant is 0. If its determinant is 0, then it implies that there is some x not equal to 0 for which Ax equals to 0, such that this is there exists symbol. And this is, of course, implies. For instance, this is a matrix A, and this matrix A times 2, negative 1, 6 equals all zeros. And the determinant of this matrix is, in fact, 0. It is a singular matrix. It's not a full rank matrix, in other words. Okay, now in this lecture, we'll do eigenvalues and eigenvectors, characteristic polynomial of a matrix. This actually is kind of a review because you would have done this in 540 or any other previous undergraduate course. Multiplicity of eigenvalues and defective and non-defective matrices. Excuse me. Triangular matrices. Determinants from eigenvalues. Hermitian and symmetric matrices. Similarity transformation, shifts, and inverses of matrices. So, definition. We are given a n by n square matrix A. Let V and lambda be a vector and a scalar such that AV equals lambda V. You know our notation, uppercase bold is matrix, lowercase bolds are all vectors, column vectors, unless otherwise specified, and straight lowercase, usually italics or Greeks are scalars. Anyway, so the solution of this, AV equals lambda V, the n by 1 vector V is called the right eigenvector. And the lambda is the right eigenvalue. When I say eigenvector and eigenvalue, by default, I mean right eigenvector and right eigenvalue. Now, usually the eigenvectors are normalized so that the Euclidean norm of the eigenvector is 1. So eigenvectors are normally unit vectors. That's the usual convention, you'll see. And eigenvalues and eigenvectors occur in pairs. So we can have multiple, in general, we will have multiple eigenvalues and eigenvectors, and they occur in pairs. So for this eigenvalue lambda, this is the corresponding eigenvector, and vice versa. For this eigenvector, this is the corresponding lambda. This lambda could have multiple eigenvectors too, you'll see. Okay, so lambda V is called an eigenpair. Thank you. So an n by n matrix has up to n eigenvalues. And the eigenvalues are usually sorted, so we index them in non-increasing order. So the decreasing, this is the eigenvalue with the highest absolute value, lambda 1. This is lambda 2, lambda 3, and so on. So lambda 1 is greater than or equal to lambda 2, absolute values that is, and so on. And so these are the corresponding eigenpairs. The spectrum of the matrix is the full set of eigenvalues. The spectral radius of the matrix is the maximum value of the absolute value of lambda I. And that's, if we follow this convention, then it's lambda 1, absolute value of lambda 1. So when sorted in non-increasing order, the spectral radius is lambda 1 absolute value. Now, suppose V transpose A equals lambda V transpose. Suppose there exist lambda and V such that this equality holds. This time I'm pre-multiplying V transpose with A. Then this lambda and V are the left eigenvalue and left eigenvector. Okay? But throughout this course, we will do right eigenvalue and right eigenvector, and that's the default. Okay, the characteristic polynomial. Eigenvalue and eigenvector are lambda and V, so that AV equals lambda V. Okay, this is the definition of eigenvalue and eigenvector of the matrix A. Since AV equals lambda V, lambda V minus AV equals 0. This is actually vector of 0, so I should have bolded this out. Hence, I take V common, lambda I minus A times V equals 0. So V is a non-zero vector, correct? But this matrix, lambda I minus A times V equals 0. What does it mean? It means that lambda I minus A, we just saw that, is a singular matrix. It's got a zero determinant, right? And so the determinant of lambda I minus A equals 0. Okay. The characteristic polynomial is this determinant. Now lambda is a variable. Okay, and so this determinant will be of degree n. It will be a polynomial of degree n. The highest power of lambda will be lambda to the n. And the eigenvalues are the roots of lambda I minus a determinant, equated to 0. So those will give you the roots. For those values of lambda, the determinant, this determinant will be 0. Okay, and therefore once you get the eigenvalues, solve for the characteristic polynomial equals 0, get the eigenvalues, and I'll give you an example, and then you'll get the eigenvectors. You'll see shortly how. Here's an example. Let's find the characteristic polynomial, eigenvalues, and eigenvectors of this simple matrix 1, 2, 2, 1. Lambda I minus A equals lambda times I, the identity matrix, minus A, which is equal to this here. Lambda minus 1, negative 2, lambda minus 1. So its determinant is equal to this, which is equal to lambda minus 1 squared minus negative 2 squared, which is negative 4, and this is lambda squared minus twice lambda minus 3. Factorize it, we get lambda minus 3, lambda plus 1. So this is the characteristic polynomial. What are the roots of the characteristic polynomial? 3 and negative 1. So the eigenvalues of this matrix A are lambda 1 and lambda 2 equals 3 and negative 1. Did you have a question? Let the eigenvectors for lambda 1 equals 3 and lambda 2 equals a negative 1 be b1 and b2. So let these be the two eigenvectors, and next we'll find out what these eigenvectors are. So for lambda 1 equals 3, the eigenvector is v1. So let v1 equals ab. Okay? And we know this is the matrix. Now we have to find the values of a and b. So lambda 1 I minus a times v1 equals 0. By definition, lambda 1 b1 are an eigenpair. So this is equal to 0. Whence, this is lambda 1 minus a, and this is v1 is ab equals 0. And replacing lambda 1 with 3 here, and then doing this matrix multiplication, we get these pair of equations. Twice a minus twice b equals 0, and negative twice a plus twice b equals 0. So the solution is a equals b. Now we have two variables, and we just got a equals b. Okay, so we have one variable free. So what we can do is, it's our choice. We can let v1 be 1, 1 or negative 3, negative 3. As long as a is fixed, then b has to be equal to a. So ab are 1, 1, negative 3, negative 3, 0.2, 0.2, or anything you like. But like I said, the convention is we want v1 to be a unit vector. So let's make a equals b equals 1 over square root of 2. And so v1 equals 1 over square root of 2 times 1, 1. We could have let a equals negative 1, 2, in which case we could have gotten, instead of v1, negative v1 as the eigenvector. In fact, eigenvectors are simply directions. Okay? Their lengths, or if you flip them to the other side by taking the negative, it doesn't matter. It still remains an eigenvector. Yes?
But sir, you have mentioned that for n cross n A matrix, there will be n eigenpairs.
Yes.
But in this case, the A is equal to B.
Well, this is for lambda 1. I haven't gone to lambda 2 yet.
But for lambda 1, V1, we can take infinite V1, not one unique V1.
That's what I'm saying. It's just a direction.
Oh, okay.
So v1 is 1 over square root of 2, 1, 1. Now, for lambda 2 equals negative 1, the eigenvector is v2, and we can likewise solve it. We get a equals negative b. And this gives us this v2, a unit vector. So our eigenpairs are these 3, 1 over square root of 2, 1, 1, and negative 1, 1 over square root of 2, 1, negative 1. Eigenvalues of triangular matrices. So the eigenvalues of a lower triangular matrix L are the diagonal elements Lii. Likewise, for an upper triangular matrix, the diagonal elements of this upper triangular matrix U are uii. Those are the eigenvalues. Here's an example. This is a lower triangular matrix. And the diagonal elements are, what are the eigenvalues of this? The diagonal elements, negative j, 2, and 3. Sorry, negative j, 2, and 1. But we would like to sort them. So lambda 1 equals 2, lambda 2 equals negative j, and lambda 3 equals 1. Characteristic polynomial. So we have this n by n square matrix A. The characteristic polynomial, like we already saw, is of degree n. Okay, so this is the characteristic polynomial, general form of the characteristic polynomial. Lambda to the n plus alpha sub n minus 1, lambda to the n minus 1, all the way to alpha 1 lambda plus alpha naught. This is our characteristic polynomial. Now, I say that there are n eigenvalues, okay? So these are the factors, lambda 1, lambda 2 until lambda n, okay? And so what I'm doing here is I'm following unique indexing. So even if lambda will have a, this P of lambda has a double root or a triple root, I will call them lambda 1, lambda 2, lambda 3, or lambda 7, lambda 8, lambda 9, if it's a triple root. Okay, so that's called unique indexing. Otherwise, we can rewrite this characteristic polynomial as lambda minus lambda 1 to the mu 1. That's the number of times it repeats. Mu 1 could be 1, 2, 3. Likewise, the next factor is lambda minus lambda 2 to the power of mu 2. Again, mu 2 could be 1 or it could be more than 1. This is when I'm following non-unique indices for the eigenvalues. So lambda 1 is a multiple root if mu 1 is 2 or 3, or as long as it's not 1. Likewise for lambda 2. Okay, what's the degree of this polynomial? I have to sum up mu 1 plus mu 2 and so on. If I add them up together, I'll get the degree of the polynomial. So anyway, this is, if I follow non-unique indexing, then this is my characteristic polynomial. P of lambda is product of I lambda minus lambda I to the power of mu I. Algebraic multiplicity. Mu lambda I is the number of times lambda I is a root of P of lambda in this. So mu I is, this is the algebraic multiplicity of lambda I, mu I, or mu of lambda I. And of course, summation mu I should be equal to n, the size of A. Geometric multiplicity. Now, even if an eigenvalue is repeating, so it has a multiplicity that's more than 1, it still might have different eigenvectors, or it might have, let's say mu 1 is 2. Lambda 1 is therefore repeats twice, right? But it could have V1 and 2 different eigenvectors, maybe V1 and V1 prime. Okay, so the geometric multiplicity is consider this space, we take all the eigenvectors V of lambda I. So this is the definition of the eigenvector, right? And so the dimensionality of the span of V, so suppose V are different vectors and we try to represent any high dimensional point vector linearly as a linear combination of all the V's. Okay. So that gives us, this dimensionality is the geometric multiplicity. Okay. So if the algebraic multiplicity is mu I, then the geometric multiplicity can never exceed mu I, because at best you can have mu I number of different eigenvectors. So this is the geometric multiplicity of this eigenvalue lambda I. So that's the number of linearly independent eigenvectors Vi of lambda I. Algebraic multiplicity is always greater than or equal to geometric multiplicity. Or mu of lambda I is always greater than or equal to gamma of lambda I. Let's look at an example here. So this is my matrix A. P of lambda is lambda minus 2 squared times lambda minus 1. You can actually guess that this would be the characteristic polynomial because we know that the eigenvalues are 2, 2, and 1. Why? Because this is an upper triangular matrix. So lambda 1 equals 2 and lambda 2 equals 1. Let's look at the algebraic multiplicities. Mu of lambda 1 equals 2. Mu of lambda 2 equals 1. These are the algebraic multiplicities. Now let's look at the geometric multiplicities. Okay, so we'll consider lambda 1 equals 2. What is the geometric multiplicity of this? In other words, how many eigenvectors does this lambda 1 equals 2 have? So let's call it V1 equals A, B, C. So I plug in the values of A and V1 equals here. It must follow A times V equals lambda 1 times V, and solving I get this. Whence this is what I land up with. B equals C equals 0. Okay, so B equals C equals 0. So all we are left with is A, and we're scaling it up or flipping its sign doesn't make a difference, right? They're all the same eigenvectors. So B1 is 1, 0, 0. That's the only eigenvector corresponding to lambda 1 equals 2. Okay, so this is repeating twice. But the geometric multiplicity of this lambda 1 equals 1. It has only one eigenvector. It has algebraic multiplicity of 2. And of course, lambda 2 equals 1. And it cannot have two eigenvectors. It can only have one eigenvector. In fact, this is what we would get if we solve for V2. This is a unit vector. That's why you see this 1 over square root of 46. 6 square plus 3 square plus 1 square is 46. So the geometric multiplicities are a 1 in both cases. Here's another example. This is our A, and it turns out that the characteristic polynomial is this. What are the eigenvalues? 4 and negative 2. And the algebraic multiplicity of 4 is 2. Right? So lambda 1 equals 4 and V1, if you solve this, you can see that you'll line up with two different V1s. So lambda 1 has a geometric multiplicity of 2 also. So mu of lambda 1 equals 2 from here, and gamma of lambda 1, the geometric multiplicity, is also 2 because we have 1, 2 eigenvectors. And of course, lambda 2 equals negative 2, you can have only one eigenvector, which is 1, 1, 2. Note that I haven't normalized it here. Okay, it's just a standard convention to normalize it. Here, I could have normalized this by dividing this with 1 over square root of 2, 1 over square root of 2, and dividing this with square root of 6. It's a good idea to normalize the eigenvalues, the eigenvectors. So these are for lambda 2, the algebraic and the geometric multiplicities. Defective matrix. This is the characteristic polynomial, and summation of the algebraic multiplicities of the eigenvalues should be equal to n. Now, I said that the algebraic multiplicity is greater than equal to the geometric multiplicity, right? So mu of lambda I is greater than equal to gamma of lambda I. However, if the geometric multiplicity is less than the algebraic multiplicity, as we saw in one of the previous examples, then the matrix is called a defective matrix. Okay, so we want the algebraic multiplicities to be equal to the geometric multiplicities for a non-defective matrix. In other words, summation I of gamma I should be equal to n for a non-defective matrix. In fact, a singular matrix could be non-defective. Okay. It will just have a lambda 1 equals 0, or one of the eigenvalues would be 0. So the eigenvectors of an n by n non-defective real symmetric matrix span an n-dimensional space. So if you're given a non-defective matrix, the eigenvectors would span n dimensions. In other words, they can act as basis vectors in n dimensions. So if this is x, then y equals ax is also n-dimensional. But note that even if A were a singular matrix, it could still have, it could still be non-defective. It'll have n different eigenvectors. Here's an example of a defective matrix. We saw this, right? This was the previous example, 1, 0, 0, and negative 6, 3, 1. These are only two eigenvectors for this 3 by 3 matrix. So this is a defective matrix. V1 and V2 span a two-dimensional space. This is an example of a non-defective matrix. We have one of the eigenvalues has a multiplicity of 2, algebraic multiplicity of 2. That's lambda 1 equals 4. But it has two different eigenvectors. And for lambda 2 equals negative 2, V2 is 1, 1, 2. I haven't normalized these again. But so here we have three different eigenvalues. Eigenvectors. So the three eigenvectors span a three-dimensional space. They're not linearly dependent. Yes?
These eigenvectors, if they are independent, they are always orthogonal as well.
Did I say that they're orthogonal?
No, because just to span the whole thing.
They need not be orthogonal. You can, in general, have a non-orthogonal coordinate system.
Okay.
So the determinant of a matrix is the product of its eigenvalues. So the determinant of A is product of lambda i's. Proof. I'm using unique indexing here, lambda 1, lambda 2, until lambda n. Okay. So now, this is my characteristic polynomial. Right? I can express my characteristic polynomial in this manner. And lambda here is the variable, and the roots are lambda 1, lambda 2 until lambda n. Right? Let lambda equal 0. Then what will happen? On the left hand side, I get negative a determinant of that. And on the right hand side, I have negative lambda 1 times negative lambda 2 dot dot dot, which is negative 1 to the n times lambda 1, lambda 2, product of the eigenvalues. Whence, determinant of negative lambda equals this. Negative 1 to the power of n times the product of the eigenvalues. Whence, the determinant of A is minus 1 to the power of n times the determinant of negative A, which is the product of, because negative 1 to the n times negative 1 to the n is negative 1 to the power of 2n, which is always 1. So it's equal to lambda 1, lambda 2, dot 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 lambda n. So we just proved this. Now, we'll shortly see what is the condition for the eigenvectors to be orthogonal. The trace of a matrix is the sum of its eigenvalues. So we know that what's the trace of a matrix, right? It's the sum of the diagonal elements, and that's equal to the summation of the eigenvalues. And we can actually see it for one of these 1 plus 7 plus negative 2 is 6, right? Yeah, so there's some typo here somewhere. Yeah. The eigenvectors Vi and Vj of two distinct eigenvalues, lambda I and lambda j, that is, they are distinct because lambda I is not equal to lambda j, are linearly independent. So if you have two different eigenvalues, no way can they have the same eigenvectors. And that's trivial to prove. You can try to prove it yourself. So if lambda I is not equal to lambda j, then Vi is not equal to Vj. And actually they cannot be negative. Vi cannot be equal to negative Vj either, because that would give the same direction. Hermitian matrices have real eigenvalues. Let's prove it. The eigenvalues of a Hermitian matrix are real. So when is a matrix a Hermitian matrix? When it's equal to its conjugate transpose, correct? So suppose we have a Hermitian matrix A, therefore A equals A conjugate transpose. Then by definition, AV equals lambda V for any eigenpair lambda V. Let's pre-multiply both sides here with conjugate transpose of V. So V conjugate transpose AV equals lambda V conjugate transpose V. We'll call that equation 1. Again, we start with the definition AV equals lambda V. Let's take the conjugate transpose on both sides. So AV conjugate transpose equals lambda V conjugate transpose, and we open up the parenthesis. Therefore, we have to swap the order of appearances. So V conjugate transpose A conjugate transpose equals lambda conjugate. Its transpose is meaningless because it's a scalar. V conjugate transpose, or this is what we have. Okay, now since A conjugate transpose equals A, we'll end up with this. That's given, it's a Hermitian matrix. Now, let me post multiply both sides with V. So here I have V conjugate transpose AV equals lambda star, or lambda conjugate, times B conjugate transpose V. And this is my equation 2. Look at the left-hand side of equation 1 and equation 2. The left sides are equal now. What's the difference? Here we have lambda, and here we have lambda star. Okay, so lambda times this equal to lambda star times this. Whence lambda equals lambda star. In other words, when is lambda equal to lambda star? When it doesn't have an imaginary part, or the imaginary part of lambda is 0. Therefore, it's a real scalar. Okay, so a Hermitian matrix has only real eigenvalues. Next. Symmetric matrix will have orthogonal eigenvectors. A real symmetric matrix. Okay, so a real symmetric matrix, and of course it's non-defective. Throughout this course, we'll assume that we're dealing with non-defective matrices. So we have to show that the eigenvectors are mutually orthogonal. That is, if Vi and Vj are two different eigenvectors, Vi transpose Vj equals 0. Okay, now this is, suppose I equals j, then what's Vi transpose Vi? It's the square of the L2 norm of Vi, correct? When Vj equals Vi. And since we are normalizing all the eigenvectors, their lengths are 1. So Vi transpose Vj is 0, that is, they're orthogonal when I is not equal to j, and it's 1 when I equals j, because then this is the square of the length of Vi, and Vi is a unit vector. And this, the shorthand notation for this is delta ij, the Kronecker delta. This is the definition of the Kronecker delta function. Let's try to prove it. So let lambda ivi and lambda jvj be two eigenpairs, and they have different eigenvalues. Lambda I is not equal to lambda j. Okay, so Vi is not equal to Vj. We saw that previously. By definition, Avj equals lambda jvj. This we have to show, right? Vi is not equal to Vj. That's what we, Vi is not equal to Vj. We saw that from a previous lemma, which we didn't prove because I remarked that it's very trivial to prove. But what we're going to show is that Vi and Vj are orthogonal to one another. That is, Vi transpose Vj equals 0. So by definition, Avj equals lambda jvj. What do I do next? Pre-multiply both sides by Vi transpose. So Vi transpose Avj equals lambda jvi transpose Vj. This is equation 1. Next, Avi, I start with the other eigenpair. So by definition, AVI equals lambda IVI. Take the transpose on both sides, and I get this. VI transpose A transpose equals lambda I VI transpose. But what can I say about lambda transpose? We are looking at a symmetric matrix. So lambda A, did I say lambda transpose? A transpose, I meant. A transpose equals A. VI transpose A equals lambda I VI transpose. Post multiplying both sides with Vj, I get this. Let this be equation 2. So this is equation 1 that I had, and this is equation 2. What can you say about the right-hand sides and the left-hand sides? The left-hand sides are the same, correct? From 1 and 2, this is what I have. But lambda j and lambda I, we assumed that they are different, correct? Because they are two different eigenvalues. So when will they be both equal? That's only when Vi transpose Vj, the inner product of Vi and Vj is 0. In other words, that's when Vi and Vj are mutually orthogonal. So Vi transpose Vj equals 0. Okay? So we showed this. This is the definition of a similarity transformation. So B is related to A via this similarity transform. For some non-singular matrix T, this is what we say. A is similar to B, and this is the similarity transformation. Okay. Now, for these similar matrices, what can we say about their eigenvalues and eigenvectors? Let B equals T inverse AT. And let's consider an eigenpair lambda V of B. Then the corresponding eigenpair of A will be lambda times TV. So lambda does not change due to similarity transformations. Only the eigenvectors change. Proof. So let's take this eigenpair lambda V. By definition, we have BV equals lambda V. Now B is equal to T inverse AT. So T inverse AT, V equals lambda V. Pre-multiplying both sides with T, we get T times T inverse is the identity matrix, right? So this side we have ATV equals lambda TV. Whence I apply parenthesis here, A times TV is a vector. A times this vector TV equals lambda times the same vector TV. So by definition, TV is a eigenvector of A and the corresponding eigenvalue is lambda. So lambda and TV is the corresponding eigenpair of A. Shifts. Let's say B equals A minus some scalar sigma times I. Can you see what's happening here? A is some square matrix and B equals A minus sigma I. What's happening here is all the diagonal elements of A, I'm subtracting from them this sigma here. Okay? So let V equals A minus lambda I. A minus, excuse me, sigma I. So this is, I'm shifting the matrix, and you'll see why it's called a shift. So let lambda V be an eigenpair of A. Then the corresponding eigenpair of B is lambda minus sigma minus V. Sorry, lambda minus sigma V. So the eigenvalues will all shift by this amount sigma. When I subtract sigma from all the diagonal elements of the matrix, then the eigenvectors remain unchanged. The eigenvalues will shift by the same amount sigma. Proof. Again, by definition, AV equals lambda V, because lambda V is an eigenpair of A. So AV minus sigma V equals lambda V minus sigma V. I'm subtracting sigma V from both sides. Whence A minus sigma I take V common here, times V equals, here I could have taken lambda minus sigma common here, which I just did in the next step. So what can you say? This shifted matrix is A minus sigma I. So this shifted matrix times V equals lambda minus sigma times the same V. So V is a eigenvector of this shifted matrix B. And lambda minus sigma is the corresponding eigenvalue. Correct? So that proves this little lemma here. Eigenpair of inverse of a matrix. So given a matrix A, and let lambda and V be the some eigenpair, then the corresponding eigenpair of A inverse is lambda inverse, or 1 over lambda, it's a scalar, V. So when you invert a matrix, the eigenvectors don't change. The eigenvalues, you have to take the multiplicative inverses, 1 over lambdas. Proof. AV equals lambda V. Again, we start with the definition. Lambda V is an eigenpair of A. Now, what we do, we just take A inverse. So A inverse A V equals lambda A inverse V, and of course this is equal to the identity matrix, whence V equals lambda A inverse V, whence A inverse V equals 1 over lambda V. So by definition, V and lambda inverse form an eigenpair of A inverse. Any questions so far?
So the eigenvalue is actually, when we have the eigenvectors, the eigenvalue simply multiply with the eigenvector and simply stretch the eigenvector in particular direction.
We haven't gone to that yet.
Okay. Because I was just having a question that in the case of
Well, we haven't gone to that yet.
Okay.
Right.
You mentioned about left eigenvalue and left eigenvector. Usually use right eigenvalue.
Of course, yes.
What is the use of this left eigenvalues and eigenvectors?
Well, there are lots of uses.
Oh, I mean, I haven't seen it in
There are lots of uses.
different, like when it comes to the application, we have to use it.
Yeah, usually for proofs we use right eigenvalues and eigenvectors, but sometimes we are forced to use left eigenvalues, left eigenvectors.
But when it comes to the application, the operation is entirely different. the output is different.
Yeah, you'll get different outputs. It's not like they're the same. No. Left eigenvalues will be different. Okay. So AV equals lambda V. That's the left eigenpair, which is the default, and V transpose A equals lambda V transpose. That's the right eigenpair. I don't remember any specific application. Of course, of like just this very moment, I cannot think of any specific application, but there are tons. For a lower triangular matrix L, the product of the diagonal elements are the eigenvalues, and same with a upper triangular matrix. And the convention is we let all the eigenvectors be unit vectors. And this is the convention for indexing. And we can follow non-unique indexing or unique indexing. If we follow unique indexing, then we have lambda n. The spectral radius of the matrix is the highest absolute value, lambda I. Characteristic polynomial P of lambda is the determinant of lambda I minus A. Lambda is a variable here, and it can be expressed in this manner. Again, this is using unique indexing. That's why I have lambda sub n here. And the roots, or if I use non-unique indexing, then I can write it in this manner. Lambda minus lambda 1 to the mu 1, lambda minus lambda 2 to the mu 2, and so on. Suppose mu 1 is 2, then that means this lambda 2 is actually the same lambda 1 here. Okay, don't confuse. And so on. And, oh, we didn't do this. So this is the characteristic polynomial, and the algebraic multiplicity is the number of times lambda I is a root of P of lambda. That's mu of lambda I. That's the algebraic multiplicity. And the geometric multiplicity is gamma of lambda I, which is number of linearly independent eigenvectors Vi. And this is always true. The algebraic multiplicity is always greater than or equal to the geometric multiplicity. And what do we want? We want, for a non-defective matrix, they have to be equal. All eigenvalues will exhibit this property. The determinant of a matrix is the product of its eigenvalues. For a Hermitian matrix, the eigenvalues will be always real. Real, symmetric, and non-defective matrix, symmetric matrix basically. Non-defective is the default in our course, and again, very rarely we'll be dealing with complex matrices, so real is kind of default. A symmetric matrix has mutually orthogonal eigenvectors, which is expressed in this manner. Vi transpose Vj is equal to this Kronecker delta, delta ij. This is when A and B are related via a similarity transformation, in which case the eigenvalues will remain the same, the eigenvectors change according to this. For shifts, if B is a shifted version of A, then the eigenvalues get shifted. The eigenvectors don't change due to the shift. And I'll give you a nice way to use this shifting property in just a minute. So for an inverse, what happens? eigenvalues, you have to take the reciprocals of multiplicative inverses, lambda inverse. 1 over lambda, eigenvectors won't change. Now, see, the determinant of the matrix is the product of the eigenvalues. Now, suppose the matrix is poorly conditioned. It's close to singular. So its determinant is a very small quantity, correct? So numerically, you're not sure what the determinant would be or how close it would be to a singular matrix. Okay, so to improve the condition number of the matrix, we can do this shifting. So what will happen if we add a tiny amount sigma to, instead of negative, I'm assuming plus sigma, lambda plus sigma. Okay, the eigenvectors don't change, but the eigenvalues, the same sigma will be added to the eigenvalues. I'm just adding sigma instead of subtracting. Okay. Now what will happen to the determinant? If the determinant is close to 0, very close to 0, numerically very small, then it will improve, right? So for a lot of numerical applications, that's usually what's done. You add a small 10 to the minus 5 to all the diagonal elements of the matrix. And then it improves the condition number. Any other questions? Do we have any other questions? Okay. So